Thank you very much. As Daniela said, my name is Chrisitan Anderka. I'm working for Intel and I support Fujitsu. You may have heard about that company. They actually do have a big development center west of Munich in Augsburg. They still produce their own motherboards and manufacture systems there. So my day job really is supporting that customer with their IT developments. Now today's topic is from sand to silicon circuits. Some of you may have asked yourselves the question, so how are chips made? How is that done? What is happening inside Intel fabs? And I'm trying to explain this within the next 30 minutes or so. So it all starts with sand. Most of you know that sand consists mostly of silicon, not the silicone, but the silicon, silicium. And it's purified. It's actually melted into a so-called ingot. That's actually done by a third-party company, for example, south of Bavaria, Wacker. Siltronic is doing this, and then they create those huge silicon pieces. I've brought a pretty old one because that's really small in diameter, and it's just the top of the silicon ingot. And I hand it around, but I really need you to promise me that you don't let it drop because it belongs to a colleague of mine, and if I bring it home broken, I'll have big trouble. But this is actually how such a silicon ingot looks like. The interesting part about silicon ingots, I had it still, the interesting part about silicon ingots is they are absolutely pure, and the crystalline structure is also very there's no impurities in it, and the crystalline structure is very, very regular. The goal really is to get a monocrystalline ingot with the most regular structure you can get out of those machines. There's a whole lot of electricity needed to do this, lots of heat and complicated processes. But again, not done by Intel. We buy products based on that silicon ingot. And that is actually shown on my next slide. So with that big ingot, what is happening, it's actually cut in dishes, or we call them wafers, very thin glass-like wafers. Those wafers are the material we buy from companies like Wacker and other companies around the world, and that's the basis we start our processor or silicon circuit manufacturing from. Again, obviously, the slicing is a difficult process because you want to have the finest and cleanest surface possible in order for the Intel fabs be able to build circuits on them. Now, in the next step, if you have this wafer, we actually start by applying photoresist. But let me take one step back. Many people think that silicon manufacturing might be a very mechanical process. It indeed is not. It's a chemical process mostly. What we do with those wafers is a whole lot of applying photoresists, applying different elements, different gases, different solutions to the wafer. So you could view a silicon facility, silicon fab facility, mostly as a chemical factory, which it really is. So one of the first steps is to put on applying photoresists. The reason we do this is they get exposed with light later on, and then parts of that parts of the photoresist that were exposed with the light might harden, and the parts that were not exposed with light, they might still be soft and be washed away. So parts of the wafer are coated after the washing away with the photoresist, and other parts aren't. That gives you a structure, and then you can apply additional materials on that wafer. You can basically put it, for example, in a chamber with gas, and the gas will then change the structure of that silicon wafer, but only on the parts where there is no photoresist anymore, the parts that weren't hit by light, okay? Now, you might think, wow, that sounds quite easy. That's a little bit like the old slides projecting, photos that were taken with slides. You have a projector, you project that image on a wall, and you can see the slide, the photo. And that's actually very similar. The difference here is that the structures that we're trying to build with the photoresist and the lightning that goes through the masks, so to say the slide, is actually quite a difficult process because we're running out of light in the process technologies. So in the past, it was an easy thing. You had a rather big chip. The structures we produced on silicon were comparably big. But nowadays, we've gone down to so small structures that the structures are actually smaller than the wavelength of the light we're using. And that's quite a challenge. And my comparison for that one is, if you're supposed to draw a fine line on paper, you would certainly pick a thin pencil, maybe a 0.3 pencil, to draw this really fine line. But in this case, all you get is a fat adding pen, and you're supposed to draw a really fine 0.3 line with this adding pen, and now you have to find tricks on how you do this. And some of the tricks we do is optical proximity correction, which is basically you create a mask that looks very different from what you actually want to create, or you do multiple patterning, so you actually use light and the photoresist process several times, or, and that is actually one of the most complicated things we do with regards to the lightning process, we have masks that have a certain determined depth, and we use the interferences of the light waves that go through the mask in order to reduce the wavelength of the light behind the mask and create the structures that we really want to create. Okay? So this is one first important step to understand when we do start the silicon manufacturing process. A whole lot of the processes use photoresist and exposure through light in order to coat parts of that wafer. Now, as I already said, one way of altering the surface of the wafer, and that's actually the first step that we do, is ion implantation, because we want to have the surface of the wafer have specific properties that we need in order to create transistors. We want them to be semiconductors, so we have to change the surface of that wafer such it is actually according to our needs. Now, ion implantation is basically something where we put that wafer coated with photoresist into an oven, and then the gas goes in with the ions, and the ions basically implant themselves on the surface, and that's one big step in the beginning of the silicon manufacturing. After that ion implantation, the photoresist is being removed, so now you have parts of that wafer with ions implanted and other parts that don't have those ions implanted. The parts that were protected with the photoresist don't have the ions. The parts that were not protected have the ions. And that actually is the beginning of the transistor formation. I think most of you will know what a transistor is. It's basically a switch, and that's the simplest element in a processor. In order to do calculations, we have many of those transistors in one processor. Depending on the type of the processor, it could be up to 1 billion or even more than 1 billion transistors in just one processor. So it's kind of hard to wrap your head around that concept of having 1.7 billion transistors in one processor. So those transistors really need to be very small. And in order to show you how small they are, I have a little video that one of our lead scientists actually did in order to explain how small those transistors really are. Let's see if the video works. And hopefully also the sound works. I think we restart with a little bit more volume, right?
There were 1 billion transistors on this single chip. Unfortunately, they are far too small to be seen with the naked eye, which means there's only one way to do this. Mr. Director, I'm ready for my close-up. to 20,000 times smaller. And just to give you some point of reference, this huge object off to my right, that's the chip I just dropped. And this large, unidentifiable object off to my left, that's a human hair, approximately 100,000 nanometers in diameter. Believe it or not, I'm still far too large compared to a 22 nanometer transistor, giving you a meaningful demonstration. So, here we go again. Okay, that's better. I'm now approximately 100 nanometers tall, or about 20 million times smaller than my actual size. At this scale, a human red blood cell would be about as tall as a 5-story building, and I would be just the right size to demonstrate some of the attributes and functions of a single modern transistor.
Okay, I hope that gives you a good idea of how small those transistors really are. If a red blood cell is as big as a 5-story building, and that guy who was shrunken down to that little size is even much bigger than a transistor, because what he's actually doing is he's holding one of those transistors later on in his hands. The other comparison I always like to make is if you think about an influenza virus that is so big that it could eat hundreds of those transistors and it wouldn't even grow in size. So think about the dimensions we have. We're really talking about virus size parts that we're manipulating every day, 24/7 in our manufacturing facilities. Now, if we go through the different steps, and they're quite complicated, and I won't go into very much detail, but basically what we're doing in the next step is we're erasing parts of that wafer, so there's 3-dimensional structures growing. With the newest generation of our process, we actually build so-called 3-dimensional transistors. So it's not just on the surface of the wafer. We're actually, by etching away parts, we're creating fins. And then when we remove the photoresist, there's another step where we would plant the silicon dioxide gate dielectric, which is the heart of the transistor. That actually makes the transistor switch or not switch. We do have polysilicon gate electron applied to that one, and then there's an insulator on top of it. I won't go in all of those details. If you want to, we can discuss this later on in the networking part of this evening. But just so you know, there's hundreds of steps that need to be taken in order to get to the transistor level. And the transistor level really is the very bottom level of that wafer, the first layer where the transistors sit. And then there is more steps applied where we put in, for example, an high-K gate dielectric, and there's also a metal gate applied in order to make this transistor switch the way we want it with the features we want it. And obviously, then once the transistor is done, we also need to connect it electrically to the outside world, or at least to other transistors on that processor, and that's done by electroplating and post-polishing and eventually creating the metal layers, which are several story high electrical wires that connect the different transistor connections to each other, transistor from transistor, but also to the outside world through the package. If there's any questions, by the way, in between, you can always ask. Now, so we've actually fast-forwarded through this manufacturing process, and what I brought with me is one of those wafers in a modern size. So you may have noticed the ingot that I handed around was very small in diameter. The 300 millimeter wafer size is what we're currently using. So going back to that ingot, that would be an ingot with this diameter and about 2 meters high. That's what we get. Then they slice wafers out of it, and after we process it in our fabs, the front side of the wafer gets this colorful picture, and you can see here hundreds of processors on the front side of this wafer. If you take a close look, and I'll hand this around as well, please don't open the box, don't drop it. You'll see a whole lot of regular structures. In each of the regular structures is one so-called die, also one processor, one CPU. Obviously, it's not a whole lot useful on that wafer. We need to package it, and that's actually then the next manufacturing steps that I'm explaining. So the left-hand picture basically shows, okay, on the wafer, we're starting to test those dies because the process is so complex and it takes so long that not all dies are good. So we work towards so-called perfect wafers, and we sometimes get them. But unfortunately, most of the time, they aren't perfect wafers. There's a few chips that don't work, so we have to test them if they work or if they don't. And then they're marked good or not good, and then they're being sliced into the little rectangles, and then the bad ones are being taken away, and the good ones are packaged. The individual die is packaged into a CPU. Yes, and you have a question. How do we differentiate? That's done with a testing machine that hooks up to connectors on that wafer. So the wafer that I'm showing here doesn't have balls attached to it, so it's nicer to look at. In reality, the front side actually gets ball connections on it, and then you see test points that you can use for those testing machines. That's a good question. Thank you. And there's another one.
Do they either work or not work, or are there performance differences?
So in this step, it's mostly checked for does it work or does it not work. But then, and that's actually, I think, let me see, maybe it's showing on the next slide, there is a so-called a process step that is called speed binning, where there's more test applied to the product in order to say, okay, what is the characteristics of this individual die and how fast can it run?
Do they name them based on that? Like, is an i5 the same as an i7, but they have different performance?
Not necessarily. Across the different marketing names we use for our processors, you might run into cases where an i5 has the same die as an i7, but it's more likely that within the i7 family, processors use the same die, and within an i5 family, you will also see mostly the same die. As a general rule, you could say that depending on the number of cores, that's a good indicator if it's going to be from the same die or not. So if you have a 4-core i5 processor and a 4-core i7 processor, chances are pretty high that this is actually from the same silicon die, but different outcome in the manufacturing process, or in many cases when our yields are really good, and yield is basically a number of how well our manufacturing works. It's mostly then just naming them differently and charging differently. Okay? Good questions. So we've packaged this individual die into a housing, and the housing's here to protect the processor, and it's also making it a little bit easier to handle it, and it's also connecting it to the outside world. So if you look at the front side of this processor package, and this is a desktop processor, you see that there is this metal cap on it. That's the so-called heat spreader. It protects the die which sits underneath. So if you look at that wafer, one of those rectangles sits underneath the metal cap. The backside of the processor has those so-called LANs. In the past we used pins, now it's LANs. It's basically contacts that are used to connect the processor to the motherboard and to connect it to the outside world. Okay. Yep, there we go. There's the class testing that I've referred to, and the speed binning that determines what type of frequency a processor is able to run. And then for the fancy parts, it's packaged in the retail package and good to be sold in computer shops. big customers like Fujitsu, they don't get the CPUs obviously in the funny, in the fancy retail packages. They get them in trays and much easier to handle when you have more units to handle. Now, this silicon manufacturing is no easy task. There's a question.
So did I get it right? It's like coincidence how fast or how good the processors are because you're determining at the beginning what are the capabilities, or like you should know beforehand like what are you actually making?
So first of all, if you look at the different processor families, there's different dies, different product really. So if you have a dual core processor or if you have a quad core processor, that's actually a different die. And also if you look at the different processor generations or the different processor brands we have, like an Atom processor, that's a totally different die from, say, a core processor. But then within a certain family, within a certain range, for example, a Core i7 with a certain number behind it might be from the same wafer as the next processor with a higher frequency. And that's determined by how well this processor was baked, if you want to use the term bake, and how capable that processor is in regards to either, for example, power consumption, which is a huge significant metric for us because notebook processors are supposed to consume as less power as possible, or if you look at, for example, the K series of processors, they are tuned towards overclocking capabilities. And for those, we look at certain parameters. Those are actually the most power-hungry processors because typically what happens is a processor is capable of consuming a lot of power. Then you can run it at a higher frequency at the cost of a higher power consumption.
So depending on the process quality, there's some kind of variation or not variation in quality or actually the output you're generating.
Yeah. So the comparison I'd like to take, and that's a very simple comparison, obviously. I think my manufacturing scientists would slap me on the hand if they heard me, but I always like to use the pizza analogy. Think about baking a pizza in an oven. Sometimes it actually goes really well. Sometimes you have a hard black edge, and sometimes you have a very wet middle. And that's kind of similar with the wafers. If our process is tuned nicely, you get wonderful pizzas. Even the edge is, nice, soft, everything works out nicely, and the middle is not wet. Still, even in such a pizza, you can use pieces that taste really good, and that's what we do. And if everything works out nicely, which is the perfect wafer I was referring to earlier, then the entire pizza is top quality and you can eat everything. Most of the time, when we talk about those yield rates or the speed binning we're doing, we can use a big portion of that wafer. It just depends then what type of product do we get out of the wafer.
So for the really high quality processors, if you want to generate them, there's a high dropout rate or throw away rate?
No. No, the idea really is we always want to have perfect wafers, and sometimes manufacturing is tuned towards a certain goal. So for example, if we want to create notebook processors, then the manufacturing process is tuned towards low power consumption. And then what happens actually is you don't get a whole lot of processors that run at high frequency, but you get a whole bunch of processors that consume very little power. And then you have to make your decision in product management where you say, okay, if I want to have a low power consumption notebook processor, I might have to sacrifice a little bit the frequency I get. So what you notice in our product portfolio is that the desktop processors that are allowed to consume a little bit more power have higher frequencies, whereas the notebook processors might have lower frequencies. Now, if you look at the features in the processor portfolio we have, meanwhile, we have pretty dynamic frequency scaling. So we allow our processors to actually speed up on frequency, for example, if they're not hot, or if only one core is used. And that's kind of a technology to offset this physical law of that you would have to have a high power consuming part in order to achieve high frequency. So with the so-called turbo features that we have in our processors, we offset that a little bit. Make sense? Okay. So as you can see, it's been quite a complicated process, and you can easily imagine that this is a very costly endeavor. A new fab for Intel is about 3 to 4 billion US dollar, and the new fabs that we're going to produce, they're more in the order of 5 billion each fab. So that's a huge capital investment in order to make that happen. But then on the other hand, that's probably the only place on Earth where you manipulate products on the atom level. And when I say atom level, I really mean this. Some steps we do here use techniques where each and individual atomic layer is deposited at the place where it should be. The tolerances in one of those transistors I was referring to earlier, there's parts in where there's a tolerance from 3 atomic layers to 7 atomic layers, and that's where we have to stay within 3 atomic layers to 7 atomic layers. That's quite a feat in order to get that. Well, as you can see, it's an expensive endeavor. We usually don't allow people in our fabs because they're very clean. And if you've seen pictures from silicon manufacturing, you see people wearing those suits. Oftentimes they're mistaken as protective suits for the people that are wearing them from chemicals or whatever. That's not the case. Actually, it's protective suits for the products we produce, because the people, with everything they lose, the coughs they make, maybe the makeup they're wearing, but makeup is not allowed in fabs, that would actually bring so much dirt into the fab that people need to wear those suits in order to protect the products from the people. What I brought with me, though, is a video that gives you a little bit of an insight of how a fab looks inside. Oops, that was too quick. So that's a fab from the inside. One of our biggest fabs in Arizona. Those little compartments transport the wafer. It's an automated system that carries wafers throughout the fab. What you'll be able to see is that they carry those packages, the orange package, and it's got a whole bunch of wafers in it, and they're always carried in one part. That's the back side of the tools. And here you can see a wafer and how they're handled from the processing machine into the compartment and transported further. Here you can see coating, applying of solution, polishing. typical throughput time of a processor through a fab is about 12 weeks. And that's one of the processes I just pointed out. Now, it's for me always quite impressive to imagine how small the things are that my colleagues manipulate in the manufacturing. If you look at how things evolved since Intel started, it's even more impressive, I think. So if you look at one of the first microprocessors, the 4008, from 1971 to a processor of today, the performance has increased 3,500-fold. The power consumption efficiency has improved in the order of 90,000 times. And the cost to produce this has been lowered by about 60,000 times. So what actually happened is that the processor cost over time roughly stayed the same. You could argue going up and down a little bit, roughly stays the same, but the number of features we put in the number of transistors we invest in one processor now has increased significantly. So have the capabilities that we obviously hope you're going to use with the software that you're coding. And that actually is the end of that introduction to how processors are made, how you get from sand to silicon circuits. I hope you enjoyed it. If there's any questions, I think I do have a few minutes more. But obviously I will be here later on as well. I think there was one from this gentleman behind. You had one, right?
You said you use UV light. So what's the current lithography wavelength you use?
So the lithography we're using is 193 nanometer. It's not extreme ultraviolet yet. We would love to use extreme ultraviolet exactly for that reason I explained in the beginning, because that would shrink the adding pen significantly. Actually now to a pen that is smaller than the lines we need to draw. Unfortunately, extreme ultraviolet light is not powerful enough yet. There's a whole lot of research happening. We're trying to implement this, but the introduction into mass manufacturing has been pushed out, and there's no date yet when EUV is going to be introduced in manufacturing. Mm-hmm.
So you're not lowering the wavelength right now? What are your next plans? What's the next step?
Well, currently we're producing 14 nanometer processor. That's our current mass production node, 14 nanometer processors. We have 10 nanometer processors in preparation. Same wavelength still. That's the magic we're doing with the masks, with the optical proximity correction, with the multi-patterning. And we're also using wet masks now, which also helps the lithography. So it's getting more complicated. The throughput time to the factory is getting longer, which causes a whole lot of problems for us in order to produce the amount of processors that we want. But these are all workarounds in lack of having source of light that is much smaller in wavelength than the 193.
Because where I asked, I heard that a couple of years ago that Intel probably will stay at 10 nanometers. Are there any plans right now to lower it even more?
Well, we've already stated plans for 7 as the next node after 10. And I think there's even a development roadmap further down. I don't know on the top of my head what the next node steps are. But we don't think yet that we're running out of gas that quickly. Gordon Moore, who is one of the founders of Intel, often was asked the question, with all the upcoming challenges, how long do you think you will be able to shrink further? And Gordon had a really good answer to that one. He basically said, think about it as driving with your car in fog. You can see maybe 50 meters, you can see maybe 100 meters, depending on the thickness of the fog you're driving through. You can always see something, and what you hope is that the road never ends. Sometimes you see a little bit further in times when you have made a major research step. Sometimes you don't see as far. So it really has been the same throughout silicon manufacturing. We never knew where the end would be, and obviously we're really spending a whole lot of money to extend that road. Currently, our spending on research and development each quarter is about $5 billion. And you had a question, right?
Actually, I have two questions. First is that nanometer number. When I was in engineering college, it was 95 nanometers that now it's down to 14 nanometers.
14 is our mass
Does that
manufacturing.
mean that the same chip that you built with 95 nanometer is now almost 90 times less size, or does it mean something different? What is the significance?
That is a very good question, but it's also a very difficult to answer question, because really what those numbers mean, they're technology nodes. The memory manufacturers, they actually had a formula on how they derived their technology node from the actual structures that they produce. For processor manufacturing, it's a little bit different. The really significant parts of a transistor, for example, which is gate length, that is significantly smaller than the technology node you're on. So if we used gate length, we would actually have much smaller nanometers today. But what it really is some sort of what do you say? Comparison to what the features are within a chip, but it's not targeting a specific feature on a transistor or on a chip. So if you say, I'm producing on the 14 nanometer technology node, you'll be hard-pressed to find a feature on a chip that is exactly 14 nanometers. But it gives you a good idea of how small the structures really are.
And completely unrelated, you showed the photograph of the Arizona facility. So that goes from being built to in production. How long does it take to clean the air inside? Do you know what the process for that is?
Actually, it's already built clean, because if you built it dirty, you would never be able to clean it afterwards. So obviously the concrete structures and everything, that's built dirty. But when you start to equip the clean room, you start clean. It's a very complicated and difficult process, also contributing to the cost of the fab. There was one more question?
Do you can expect what is the limit of gigahertz per CPU in the future?
That's a good one, because if you go back, I think 10 years or so, or maybe even more than that, one of our technical leaders said that I think by 2000, I don't get it right anymore, he wanted to go to 5 gigahertz really quickly. And then we realized if we continue on this path to have small number of cores, but very high frequency, you would quickly get to very hot temperatures, and you would also not control the power consumption of the CPU. So we actually had a chart at the time that showed, okay, if we continued on this trajectory that we were on, you would quickly get to the heat dissipation of a heat plate in your kitchen, and then quickly thereafter, if we continued on that trajectory, you would actually get to heat dissipation of the sun. Obviously not a good thing to have that kind of a heat dissipation in your notebook, especially if you think about placing it on your legs. So we had to find a different solution for it. And the solution, a big part of the solution has been to go to multiple cores, because actually if you, and this is where software comes in, this is where you guys come in, if you're actually able to program such, your software is able to use more than one core, it's multi-threaded, then you don't need the high frequency. You can actually distribute the workload on the different cores, and it's easier for us to do more cores and not go up with the frequency as high as if we would have to go if it was just single cores. Does this answer the question? Okay, cool. I guess I'm timed out. So if there's more questions, I'm here afterwards, but then I'd like to hand over to Thomas.